Dear learners, I welcome you all to this module. The title of the module is Divisors and Euclidean Algorithm. In this section, we are going to introduce the concept of divisibility and some of its important properties. And then we are going to see the definition of GCD and LCM of two integers and the method called Euclidean algorithm to find the GCD of two integers. When will we say that one integer divides another exactly with remainder 0? We shall see the answer of the question in the following section. We shall see a definition now. If a and b are any two integers with b is not equal to 0, then b is said to be divisor or a factor of a, and that a is divisible by b if and only if there exists another integer q such that a is equal to qb. We write b divides a, that is b with a line a, that is the notation to denote that a is divisible by b, and say that b divides a or a is a multiple of b. For example, 6 is a divisor of 18, minus 5 is a divisor of 35, 16 divides minus 32, minus 4 doesn't divide 37. The symbol straight line with a cross over is used to denote does not divide. Since every number is a multiple of itself, we can say 1 divides n, and also 0 can be written as 0 multiplied by n for every integer n. We can say that every integer is a divisor of 0. Now, let us see some theorems that discusses about the properties of divisibility. The first theorem, so here we have a, b and c to be integers such that c divides a. So, we have already spoken about this notation, the straight line. When you use the straight line, that means c divides a and c divides b. Then we have to prove that c divides ax plus by for any two integers x and y. So, if you have c, it is divisible by it divides a and b, then you have to prove that the same c also divides ax plus by for any x and y. So, let us prove this now. So, we are going to take c divides a and c divides b. That implies that this a can be written as some multiple of c. Similarly, b can be written as a multiple of again c. That is, according to division algorithm, the remainder is equal to 0. The remainder is 0, then you have q1 and q2, right? There exists some unique integers. So, according to that principle, I have written a is equal to q1c and b is equal to q2c. Now, for arbitrary x and y, that is integers, we are going to consider ax plus by. Now, what is a? A is q1c, I am going to substitute here, and what is b? B is q2c, I am going to substitute that also here. So, I have q1cx plus q2cy that is equivalent to c multiplied by q1x plus q2y. You can see here this q1 is an integer, q2 is again an integer, x and y are also integers. So, therefore, q1x plus q2y is also an integer, and if you multiply by an integer, whatever you are getting as an outcome, the product, that will belong to an integer. Therefore, ax plus by is an integer, and you can write ax plus by as a multiple of c. That implies that c divides ax plus by. So, we are able to prove this. So, whenever c divides a and c divides b, then c also divides ax plus by for any two integers x and y. So, now we shall prove the next theorem. So, here we are going to discuss about the relation. We are going to consider the divisibility as a relation, and we are going to prove that that is the partial order relation. So, we are going to define the relation first. R is a binary relation that is defined on n, set of all natural numbers, defined by whenever the ordered pair a comma b belongs to R, if and only if a divides b. So, this is the relation that we are defining. So, you can write A and B belongs to R when A divides B and the converse part also. For example, 2 divides 4, therefore 2 comma 4 will be in this relation R. Okay, fine. Now, we are going to prove this is a partial order. Okay, for in order to prove this relation is a partial order, we have to first prove that the relation is reflexive and the relation is antisymmetric and the relation is transitive. First, we shall prove the relation is reflexive. Reflexive in the sense that A should be related to A, that is A comma A should be here in the relation. Now, let us take A to be a natural number because it has been defined on natural numbers, and we know that A can be written as 1 multiplied by A. Therefore, A is a multiple of A, therefore A divides A. So, if A divides A, then the ordered pair A comma A will be there in the relation R. Therefore, this relation that we have defined, that is a reflexive relation. And then we have to prove antisymmetric. Antisymmetric in the sense that whenever A is related to B and B is related to A, we have to prove that A is equal to B. Okay, fine. So, now let us take A and B to be our natural numbers, and then we are going to assume A and B are related, that is A comma B belongs to R, and the similar way B and A are related, B comma A belongs to R. So, here you have to note down that, so when A divides B, this A should not be equal to 0, right. Similarly, when B divides A, this B should not be equal to 0. Have to have in your mind that this B is not equal to 0 because we are talking about the divisibility. Now, listen, from here we are obtaining A divides B, and from here we have B divides A. So, if A divides B, this B can be written as Q1A for some Q1 belong to N, and similarly this A can be written as Q2B for some Q2 belongs to N. So, now this B is equal to, instead of this A, I am going to replace Q2B, that is B is equal to Q1, in the place of A I am going to substitute Q2B. So, now as I told you earlier, this B is not equal to 0. What you can do, you can divide both sides by B, therefore you have Q1 Q2 is equal to 1. So, here Q1 and Q2 are both natural numbers, and if you multiply two natural numbers, you are getting 1. So, this will happen if and only if both of them, that is both Q1 and Q2 is equal to 1. Both Q1 and Q2 is equal to 1. Therefore, that again implies that A is equal to B. Why is it so? Because here you can see here, no, if you substitute 1 here, B is equal to A, and if you substitute here 1, A is equal to B. So, therefore, we have A is equal to B. So, we have assumed A and B are later as well as B and A are later. Then you can we proved that A is equal to B. Therefore, the relation that we have considered is antisymmetric. Now, let us prove the remaining one. Let us prove the relation is transitive. So, transitive in the sense that we have to take 3 elements. Let A, B, C belong to natural numbers. I am going to assume that A and B are later and B and C are later. I have to prove that this A and C are related to each other, that is A and C ordered by A comma C should be there in the set R. So, now since we have assumed A and B is later, I can write B is equal to Q and A, as well as since from the fact that B and C belong to R, I can write C is equal to Q2B for some natural numbers Q1 and Q2. Now, consider this C. So, C can be written as Q2B, and in the place of B, I am going to substitute Q1A. That will give me C is equal to Q2 Q1A. So, here you can see Q2 Q1 you can have, Q2 Q1 is again a natural number. So, Q2 Q1 you can have multiplied by A, which means that C is a multiple of A, that implies A divides C. Therefore, the ordered pair A comma C will be there in our relation R, which means that we are able to prove the transitive property of OR. Altogether, we are able to prove OR is a reflexive relation as well as it is antisymmetric and it is transitive, giving the fact that the OR that we have considered, that is a partial order. Now, we shall see the definition of greatest common divisor. An integer can be a factor of 1 or more integers, that is 2 is a factor of 4 and 10 and many more numbers. So, we can say that 2 is the common factor or common divisor of 4 and 10. 1 also divides 4 and 10. So, 1 is also the factor, whereas 25 and 7 has only one common factor and it is 1. We know 1 divides every integer. If we consider two integers, it may have so many common factors, but in this section we study only about the largest common divisor, which is called the greatest common divisor. Definition we shall see now. Let a and b be two given integers, not both of which are 0. The greatest common divisor, we are going to denote it by G, of a and b denoted by GCD of a and b, is the largest common divisor of a and b, satisfies the following condition. The first condition is G is a factor of both a and b, that is G divides a and G divides b. And the second condition is if C is any integer such that C divides a and C divides b, then C should be less than or equal to G. We shall see some examples. The greatest common divisor of 20 and 7 is 1, because 1 is the only number that divides both 20 and 7. We cannot have any other common divisor other than 1 that divides both 20 and 7. Similarly, the GCD of 9 and 6 is 3. 3 divides both 9 and 6, and you can see here 3 is the largest divisor, that is largest number that divides both 6 and 9. And the GCD of 15 and 30 is 15. You can have 5 also divides 15, 5 also divides 30, but here 15 divides 15 and 15 divides 30, and you can say here, see here 15 is a very big number than all the common divisors of 15 and 30. Therefore, here GCD of 15 and 30 is equal to 15. We shall see a lemma. That lemma says if A is equal to QB plus R, where A, B, Q, R are all integers, then you have GCD of A and B is equal to GCD of B and R. So, we shall prove this lemma by using division algorithm. So, now you have A and B. According to the division algorithm, you can write A as QB plus R, where this remainder R is greater than or equal to 0 and less than B. So, now I am going to denote the GCD of A and B by the notation or an alphabet called G. G denotes the GCD of A and B. Now, since G is a GCD of A and B, according to the definition, G should divide A as well as the same G should divide B also. So, since G divides B, G should divide all the multiples of B. Therefore, G should be able to divide minus QB also. So, now I have G divides A and G divides minus QB. So, if G divides A and G divides minus QB, it should divide the sum of both of them, that is G divides A plus minus QB, and you have already G divides B. So, what is A minus QB from here? From here A minus QB is R. Therefore, G divides R and G divides B. So, which means G is a common divisor of R and B. So, from here can we say that G is a GCD of R and B? We cannot say right now, right? Because we have to prove the second condition also. What happens if you have an arbitrary common divisor of B and R? I am going to take the common divisor to be D. So, I have another divisor that divides both B and R. So, now if that is the case, then D divides B as well as D divides R. So, if D divides B, then D divides QB also. So, D divides QB and D divides R. Therefore, it should be able to divide QB plus R also. Therefore, I have D divides QB plus R. So, what is QB plus R? QB plus R is equal to A. D divides A. Therefore, D is a common divisor of A as well as D is a common divisor of B, right? Okay, now what about G? G is GCD of A and B. Since G is a GCD of A and B, this D should be less than or equal to G according to the definition of the GCD of A and B. Now, coming to the fact that D is an arbitrary common divisor of B and R and the D is less than or equal to G. What does this imply? This implies that the same G is also the greatest common divisor of R and B. Therefore, GCD of A and B is same as GCD of B and R, as you don't have any other divisor, the common divisor that exceeds this G. Now, let us talk about an algorithm that will be very useful to find the GCD of any two integers A and B, that is Euclidean algorithm. Let A and B be two integers with B is less than A. I am going to have like this. I am going to have two integers and B is less than A. An algorithm, this algorithm will have a list of steps that is to be followed in order to find the common divisor GCD of two integers. The first step is, so according to using a division algorithm, what you can do is, you can write A to be equivalent to Q1B plus R1 with R1 is greater than or equal to 0 and less than B. So here you may have this R1 to be equal to 0 or it is not equal to 0, right. So, not necessarily R1 should be equal to 0. So, if R1 is not equal to 0, what you can do is, you can again write B in terms of R1, that is you can have B as well as R1 and B is equal to Q2 R1 plus R2, where 0 less than or equal to R2 less than R1. In other words, you can say, you can divide B by R1 and write the quotient as well as the remainder. And if R2 is not equal to 0, repeat the step again, that is write B in terms of R2, that is B is equal to Q3 R2 plus R3. So, you have to continue this step until you have this remainder to be equal to 0. That is, this process will surely end, and the end process where at which stage you are getting the remainder to be equal to 0, that stage here I have denoted that R by Rk plus 1. You have to continue until you get the remainder to be equal to 0. So, the last non-zero remainder, that will be your greatest common divisor of A and B. So, these are all the steps you have to follow in order to find the greatest common divisor of two integers. That is, first you have to have two integers and express them in terms of using division algorithm. The remainder is 0, then no problem, whatever you have, that will be the last greatest common divisor. But if the remainder is not equal to 0, what you have to do is, you have to divide B again with the remainder that you have got. Have to continue the procedure until you get the remainder to be equal to 0. The last non-zero remainder that you obtain, that will be the greatest common divisor of the two integers that you have considered. So, now we shall see this with the help of an example. What we are gonna do now is, we are gonna find GCD of 13 and 271 and we are gonna express the GCD as a linear combination of 13 and 271. We shall see how this can be done. So, by division algorithm, so you have two integers. So, whenever you have two integers, the division algorithm guarantees you the existence of a linear combination of 13 and 271 for that matter. So, now this 271 can be written as 20 into 13 plus 11. The process of finding this, that we have already discussed in the previous module. So, this 271 is equal to 20 multiplied by 13 plus 11, and after this procedure you can see this 11 is not equal to 0, that is the remainder that you have obtained is not equal to 0. Now, what I am going to do, I am going to have this 13 to be expressed in terms of the remainder, that is 1 multiplied by 11 plus 2. Now, again this remainder that you have obtained is 2, that is not equal to 0. Now, what you have to do, you have to express this 11 as a product of 2, that is 11 is equal to 5 multiplied by 2 plus 1. Now, again the remainder that you have obtained here is 1, that is not equal to 0. Then what you are going to do, you have to express this 2 as a multiple of 1, that is 2 is equal to 2 multiplied by 1 plus 0. At last you have obtained the remainder to be equal to 0. This step you will surely attain. So, now what is the last non-zero remainder? The last non-zero remainder is 1. Therefore, the GCD of 13 and 271 is nothing but 1. Okay, we have computed the GCD of 13 and 271. Now, the next procedure is we are going to write the GCD as a linear combination of 13 and 271. That is our next part. So, now the whatever you have obtained here, the GCD is 1. This GCD we are going to write in terms of 271 and 13. How it can be done? So, listen. So, this 1, no, from this step 1 can be written as 11 minus 5 multiplied by 2. We are going to trace it back and we are going to write in a way that we want. 11 minus 5 multiplied by 2. And again, this 2 can be written as 13 minus 1 multiplied by 11, right. So, that is you have 11 minus 5 multiplied by 13 minus 1 multiplied by 11, and after that wherever you can substitute 13 you can have or 11 you can have as 271 minus 20 multiplied by 13, and upon the simplification, very simple simplification, you will have 1 as a linear combination 271 and 13. Here we have 1 is equal to 6 multiplied by 271 minus 125 multiplied by 13. All you have to do is you have to trace the steps back of the Euclidean algorithm and write in the required form, then you will have your answer. So, from here Euclidean algorithm will be very helpful to find the GCD of two integers, as well as the same GCD can be written as the linear combination of the two integers that you have already considered. Now, we shall see the definition of relatively prime integers. Non-zero integers are relatively prime if and only if the greatest common divisor is 1. In other words, we say they are relatively prime if and only if 1 is the only positive integer which divides both the given integers. Let us discuss about a theorem. The greatest common divisor of integers a and b is an integral linear combination of them. That is, if g is equal to GCD of a and b, then there are integers m and n such that g can be written as ma plus nb. Two corollaries which follow from the above theorem are: suppose a, b and x are integers such that a divides bx. If a and b are relatively prime, then a should also divide x. By the above theorem that we have mentioned, we haven't seen the proof, but have the statement in your mind. By the above theorem, there exist integers m and n such that 1 can be written as ma plus nb, because here 1 is the GCD of a and b, as a and b are relatively prime. Now, multiply both sides by x, we get x is equal to max plus nbx. We have a divides max and b divides nbx, because max and nbx are the multiples of a and b respectively. Therefore, we have that whatever you have that will divide bx, thus you have that will divide max plus nbx, that implies that a will divide x also. The next corollary from the above theorem is: the greatest common divisor of non-zero integers a and b is divisible by every common divisor of a and b. We shall see the proof now. Take g to be the GCD of a and b. Then by the above theorem, there exist integers m and n such that g can be written as ma plus nb. Thus, if c is a common divisor of a and b, then c divides g. Next, we shall see the definition of least common multiple. So, we have already seen the definition of greatest common divisor. Now, we are going to see the definition of least common multiple. The least common multiple of any two non-zero integers is very closely related to GCD. Consider the set of all least common multiples of two non-zero integers. Then, by well ordering principle, there exists a least element and we call that as the least common multiple. That is, you have to consider a set of common divisor of the integers that has been given to you, and then out of them you have to pick the least one. The precise definition is the least common multiple LCM. We are denoting that by L here. L of two non-zero integers a and b is denoted by L is equal to LCM of a and b is a positive integer satisfying the condition. The first condition is a divides L as well as b divides L, and if a divides m and b divides m, then L should be less than or equal to m, where m is the positive integer. For greatest common divisor, we had greater than or equal to. Here, since this is a least common multiple, we have L is less than or equal to any other multiple. So, now consider this examples. LCM of 2 and 4 is 4, and LCM of 12 and 5 is 60, LCM of 20 and 20 is again 20. Dear learners, we have come to the end of this module. In this module, we have introduced the concept of divisibility and we have seen the properties by using some theorems. After that, we defined GCD and we had an algorithm called Euclidean algorithm that helped us to find the GCD of any two integers, and after that we concluded this session by seeing the definition of least common multiple and some examples of it. I hope this session would be very useful to you. We will see you in the next module. Until then, thank you.